This is the Amp Hour Podcast. Released January 10th, 2021. Episode 525. Open FPGA Toolchains and Machine Learning with Brian Faith. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
Hi, and I'm Brian Faith, CEO of QuickLogic.
Welcome, Brian. How are you doing?
Doing great. How are you, Chris?
Oh, I'm real excited to talk about some of the stuff we're going to be talking about here today. First off, I should thank Mr. Tim Ansel for introducing us. We can have like the Tim introduction series at this point. He's introduced us to so many interesting people.
It seems like he knows everybody.
It does. So maybe that's a good place to start. So how do you know Tim, and kind of what is that relevance to some of the other people that we've maybe had on the show around open toolchains and such?
Well, it's funny, and I think everybody needs a lesson in being persistent, and Tim is the right guy to teach that lesson. I think a couple years ago, he ran into us at a trade show. I was in our booth, and we were talking about FPGA technology, and he came up and he said, "Hey, I'm at Google, and we're doing this really neat open source tooling for FPGAs, and you should contribute your architecture information, and we can get you included in that toolchain." And
easy peasy.
Yeah, easy peasy, no problem. And if you know most of the FPGA companies in the world, and us at the same time, we were thinking, no way would we do that. Why would we do that? We're just giving out information that makes us irrelevant. That's a silly thing to do. So I politely declined. And then I think about a year later, he was at another trade show, and this was with some of my colleagues at that trade show. I wasn't there at the time. And he came up to the booth and he said the same thing. And, a lot had changed in that year, actually, for us. We'd started an IP licensing business, and we were looking at the future of the tools and how people design with FPGAs. And so credit to the folks at QuickLogic who were talking to me at the time. They brought it back and they said, this guy, Tim Ansel, came and he talked about this open source tooling, and we should really give this a shot and look at it. Yeah. So we did. And that started off this whole series of conversations and meetings with Tim over at Google about really what this could bring to us as a company and to the industry. And we just looked at it through a very different lens at that point, and then sort of off to the races after that. But definitely Tim was persistent. He remains persistent. And I think that's a very good thing.
Yeah. And so so the open tool chain is your official tool chain now. Is that correct?
It is. That is our official tool chain. So
that is super cool.
Yeah, it's cool. It was. It took a long time to get there. Big mindset shift within the company. It took a few quarters actually to get comfortable that was the right thing to do. But yeah, I like to tell the story that Tim, again, he sent me a note one day and he said, if you really want to see what these open source tools can do and sort of the state of the union of those, go to this OR conference in Bordeaux, and you'll see. And he kind of left it at that. So I think my CTO and I, we basically had, like a few weeks to book that trip. So we booked it, we went there, and we were just blown away at how good the tools were and what you could do, and all the future tools that sit on top of these sort of core FPGA tools that allow people to program in Python and use FPGA technology. So I'll never forget, after the first day of watching all these tech talks, we were walking back to the hotel, and we were just sort of walking in silence for a while. And then we thought, wow, there's something there. This is really, really cool. And that's sort of the start of this whole chain of events where it became the tool of QuickLogic for our FPGAs, which I think is really cool. Yeah,
that is super cool. And so I think we should also frame all this too. It's not like QuickLogic is some fly-by-night operation either. You guys have been around since 1989. You went public in 99. You have a bunch of different products in the space, and so it's not like you're some small operation either. It's like you're a public company on the NASDAQ. Yeah, so on the NASDAQ, and so it's like, okay, this is a pretty big shift, I would imagine.
It was a huge shift, and that's actually why it took us. Firstly, that's why I resisted it for a year, but then that's also why it took quite a while just to get comfortable with it, even after we really started to dig in and understand that, there's good quality results, but how much do we have to open up of our crown jewels in order to take advantage of that and enable people? And because we're public, because we've been around a long time, there's a lot of inertia, and overcoming that inertia again, took persistence, but it also took a long time just to get comfortable. And
Yeah.
we finally did.
I imagine like like legacy, legacy people or customers rather that have legacy tools and just working with that. So could you give us an idea of like what do the tool chains used to look like for your products?
Well, just as a history, a long time ago, my first job at QuickLogic was actually designing the schematic macros for people to do schematic capture for adders and counters and shift registers. So I come from that era, I guess.
Hmm. Hmm.
And then we brought on synthesis. So we were actually, I think, the first FPGA customer to work with Simplicity when they were a standalone company,
Oh, okay.
doing
Yeah.
HDL synthesis. But in more recent times, the toolchain is Mentor Graphics Precision RTL for synthesis. For simulation, it's Verilog, so any simulator will work. We didn't really bundle any simulator with our tools. And then the place and route is a proprietary toolkit we've had for quite some time. So effectively, if you're a customer, if you wanted an OEM bundle, you would buy that from us. You would get Precision RTL, OEM edition, and our place and route for that end-to-end design. And then you could use any Verilog simulator.
Yeah.
So with this new approach, basically you would use SymbiFlow. And with SymbiFlow, you can do simulation, you could do synthesis. With EOS, you can do the place and route with VPR, and then you get the bitstream creation that you can then program the FPGA with.
Yeah, that's great. Yeah, and I think my introduction to the FPGA world was always like these IDEs that were like completely like vertical as well. And so it was, I think Micro Semi was the first one where I had gone and like realized that you could, piece out these different things. But I would imagine that having that culturally would also help as well of like, having your customers understand all these different individual pieces and not having it as one, like, single IDE type of thing as well.
Yeah, it was also it's a support load to connect all these different tools
Yeah.
together and support
Yeah.
them, especially if you don't really understand the inner workings of them. So I do think having SymbiFlow as like this umbrella tool, I think that's good. It's actually better than what we had in the past. The fact that you can compile from source means that people can they have the flexibility depending on their skill set to do that, or just
Yeah.
use the binaries that we provide. I think an interesting point though for us is that this is not just about the FPGA engineer. This is about like the software engineer that may be able to
Yeah.
start taking advantage of the FPGA through the tools that are available on top of SymbiFlow. And it's also worth noting that we started as an FPGA company. Programmable logic remains our crown jewel on the hardware side, but we've embedded those in other like higher complexity devices. So we have a device called EOS. It has an ARM core in it. So now with the open source approach, we can have open source software that supports the ARM core, and we have the SymbiFlow that supports the embedded FPGA that's on the same chip. And eventually, all these will tie together so that you can sort of do hardware software partitioning, all with open source tools.
Yeah, that is super cool. And yeah, and people actually may recall we had so the Quick Feather development kit was something we gave away on the show through Crowd Supply a couple months ago, I think at this point. But that's actually a QuickLogic. That's the QuickLogic EOS is on that board that we were giving away as well. So that was,
That's right.
which I didn't even piece together until you and I started talking, at a meeting. And I was like, oh yeah, right. We've interacted in that way. So yeah,
Hmm.
yeah, and so that is super cool, and I definitely want to come back to EOS at some point because I think that's really a core, that whole IP idea and like the AI, voice recognition stuff is really interesting too.
Yeah.
On the toolchain stuff though, like so how has do you see more software engineers kind of coming into the fold and like interacting with the tools, or I guess from the application side of things? So like are the application engineers being like, oh, we're talking to more software engineers now?
Yeah, we're starting to see that. And granted, that with there's so many people coming in and buying Quick Feather, participating in these contests that we're running, and so I think there are a lot more software engineers. We don't get to interact with all of them, but we know that that's happening because we're actually seeing the software development that's happening and being pushed live. Like a guy ported NutX to it, right,
Oh yeah, okay.
on the ARM core that uses that plus FPGA. And so, like those things wouldn't happen if it was just a hardware engineer playing with the device. But that I think is one of the promises of open source is when everything's out there, you can start seeing improvements take place in the community that you wouldn't do yourself, right? Or you
That's right.
couldn't do yourself even if you wanted to. But yeah, we're definitely seeing more software engineers playing with it.
Yeah, 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 and you start to get extensibility at that point, right? You actually get some network effects, basically.
Huge network effect. In fact, on
Yeah.
NutX, I remember we had a customer about 2 years ago say, "Hey, can you port NutX to EOS S3?" And we looked at it. We weren't familiar with NutX, and we thought, well, yeah, we can do this if we have like 5 months of time, and we assign 3 engineers to it. And then there's opportunity costs, and all those things you have to go through before you commit a number of people to a project. So we didn't do it, and we said, no, we're not going to do this. But please go off and use free RTOS that we'd already had.
Yeah.
Then along came Brennan Ashton, and he got QuickFeather, and he ported NutX to it, and he actually presented it at this conference, and he did that in like a few weeks by himself. And that wouldn't have happened if we hadn't had all this stuff in the open domain, right? So
Right.
definitely huge network effect going on.
Yeah. See, I always feel like there's like a potential problem in that like anecdote, but I'm still glad that anecdote was given and that it exists. But I feel like in the wrong hands, an executive might be like, "Free stuff, yeah," But I think what it really is, it's like that feels like that's the outcome of being open versus like, you know, I feel like I've seen other examples in the past of, oh, we're gonna make an Arduino thing, and then we'll get all this community from it. But it's like, no, no, no. Actually, there's a lot of under the surface tooling and dedication to that kind of idea of being open. That's actually much more critical. I feel like, and I don't know. It feels like a nuance to me, but I always feel like that argument of like this thing might happen, but it requires so much from the company itself to be open and to actually like dedicate to that cause.
Yeah, I agree. And I think a lot of that comes back to mindset. And, we've
Hmm.
gone through that whole thing ourselves where if you're used to using or designing with proprietary tools and only putting proprietary tools out, you kind of like you use your own little sandbox for design and you can keep it to yourself. And I think it actually, now that we're more familiar with the open source development methodologies, and we're still learning, by the way, we're not all the way there yet. And we're reminded of that every
Yep.
day.
Yep.
But the more that you design out in the open, I think it actually improves the quality of the product because you actually pay more attention if people are seeing your work versus
Yeah.
just seeing the outcome, right? They see
Right.
the
Right.
sausage making. And so
Yeah.
you have to be, I think you're more careful, more diligent, but then it also opens you up to be more receptive to feedback, right? And not
Mm.
designing in a vacuum. And I do think that ultimately yields a better product.
Yeah. Yeah. No, I agree. I agree. And I think it's tough because, well, it's tough because we're humans, right? I mean, like it sucks to get criticized. It sucks to think there might be more work there. Like all of that stuff is the potential downside, but also, like you said, there are some very real upsides if you decide to go that route.
Exactly. Totally
Speaking
agree.
of downsides, so you were a little worried about it. Your investors were a little worried about it. Ultimately, what did you give up on the FPGA side of things? Like, did you just have to publish the bitstream documentation, or what else was involved with kind of getting into this software ecosystem?
Well, if you look at just for context, in order to get an FPGA architecture or device support in the open source tools, to date, most people were trying to figure out how to create the bit streams by looking at devices in the market and sort of analyzing them. That really slows down innovation if you think about it, because it just wastes so much time trying to figure out how something works rather than just somebody telling you how it works. And so what we had to do is we had to publish the spec around the bitstream and how that configures all the elements of the device, which means you have to give out some architecture information on the programming side, the routing, the logic, and all that. So it's architecture description and then the functionality of the bitstream.
Okay, and then like so, I guess give us a little historical context here then too. So why haven't FPGA vendors done this historically? Why hasn't the bitstream documentation out there? It doesn't seem like you could really do all that much. Well, I could do nothing with it, but even a competitor, what could they possibly do with that sort of thing?
Well, I think if you're really clever and you have a lot of experience with FPGA development, meaning you're actually designing the chips, the more you understand about the architecture, the easier you would have to actually go and replicate that yourself. In truth, though, the information that you're publishing to get into the tools is really how you would functionally map a design to it. It's not how you would
Hmm.
actually manufacture it at scale with good quality,
Yeah,
reliability, good yields, like all those things that are really under the hood.
yeah,
And when we came to appreciate that that was sort of the distinction, we knew that we could still protect our ability to monetize the asset and sell devices while giving the information that's needed in the open domain to actually make the tools work and target the devices with good quality results.
hmm
And so that's why we don't have to publish each and every transistor down to the, basically providing a blueprint. We don't have to do that. It's really just the information to use it.
Here's our masks for the fab and stuff like that.
Yeah,
Come on in,
exactly.
anybody.
Right.
Yeah. I mean, that's what I think about. Like, so when I think about like who's going to maybe take advantage of this information and use it, it's like, other FPGA competitors, they're probably not going to like turn on a dime and be like, oh, QuickLogic's doing like this. We're just going to go and do it all like they do. And so what I really think about is like maybe, so potentially some fabs in China might, take this IP and try and replicate it and, make similar things in a fab over there. That would probably be the biggest risk, from a IP perspective. But otherwise, yeah, I guess maybe I just don't understand the competitive landscape well enough to understand how that would impact things. But then I also think like there's got to be patents or I guess maybe it's traditionally trade secrets versus patents type of thing.
It's really more trade secrets versus patents, exactly. So I
Okay.
think as long as we maintain the trade secrets, the know-how on the manufacturing side, and the tricks that we have for tests and things like that, that's really what makes this a scalable, viable business for us still, even if we're
Hmm.
open sourcing some of the architecture information. And I mean, truth be known, like with the architectures that are already supported in the SymbiFlow from people figuring out how devices work, if your example about, Chinese companies, perhaps they could go off and do that anyway today, right? it's
Right.
not
Right.
it's not like we're enabling anything tremendously new in the sense that we're putting that information out that people already understand on other devices. It's just that
Yeah.
we're shortening the amount of time it takes for the architecture to be supported by the tools, right, and get
Yeah.
into the hands of people that can actually use it.
Yeah. No, it does seem like openness and like, scalability in that way. It's like a software scalability thing. That is the competitive advantage because as far as I understand it, you guys are fabless, right? I mean, you
Correct.
don't own fab capabilities or anything like that. So
Exactly.
if
Exactly.
anyone else had the tools to go and design, FPGA blocks and, put it all together, I mean, even there's like an open FPGA effort that's going on part of the shuttle runs, I think, as part
Exactly.
of the
With
open
the open
PDKs.
mpw. Yep.
Yeah. Yeah. And so, okay. So it seems like scale is like one of the biggest advantages that you have. Obviously, you have brand name, you have the capabilities to support customers. That's a huge one. And now you have this tool chain in there. So what's next then, I guess? I mean, usually that's the question at the end of the episode, but I'm kind of curious now because I mean, you're also talking about branching out into IP and, microcontroller based stuff as well. What do you see as this competitive landscape moving towards for QuickLogic?
So to answer that, I'll say that we think that the market to sell to software engineers, this hardware capability is actually far larger than just selling to the traditional FPGA user, A.
Yeah.
And B, I think that there's this notion now where people want to have like mass customization, right? Not everybody wants to buy the same chip that everybody else has and just put a label on it. They want some level of customization or innovation for themselves. And so if
Yeah.
you think about that, I think on the software side, like tailoring the solution for software engineers, that's going to happen over time. Just seeing all these different tools that are building on top of the SymbiFlow tool and how they're allowing different languages now to target FPGAs, like Python, for example, right?
Yep.
So I think that's going to happen over time. But this notion of mass customization, though, what that means is that a standard product that's not programmable or not customizable at the hardware level is not going to be sufficient, right? And also, they're going to have more and more companies now that want to have their own silicon for whatever reason. It could be control the supply chain. It could be that they have some secret sauce that they don't want anybody else to know about except for themselves. And if you look at what the Open MPW project's doing with Google, that whole vision there is to drive down the cost of custom chip design so that it's truly democratized and everybody can afford to do it, right? So, in order for that to really take hold, that really drives the need to have IP that's available for those custom chips. And that's why this is really sort of merging with this IP licensing initiative that we started a couple of years ago. But I think it's going to make it a much more scalable approach now because if you think about, you mentioned Open FPGA project. So if you think about what that project's doing, it's allowing you to quickly sort of customize your FPGA architecture, right? You can tailor it for certain use cases or densities or different fabs, processes. If you think about the capability of that, with this notion of openness on the software side, you can imagine programmable logic or little bits of programmable logic in almost every chip that you do, right? And so for us, we're thinking about, the future is around how do we take this core technology we have and evolve our business model and our R&D model so that we could actually afford from an opportunity cost point of view to have these devices, these architectures, and all these different process nodes in different fabs around the world, which to me, that's the huge scale point, is where we're not limited by just our sales and marketing and operational side from a device sale point of view, but how do we scale that so that our IP is in everybody's devices, right?
Mm,
That's, to
yeah.
me, that's the huge upside.
Yeah. I mean, when you look at IP in the first place, right, it's just like, I mean, well, first off, hardware is not super high margin and software is much higher margin. When I think about IP, it's almost, well, if you'll excuse the almost, it's extremely high margin, right? It's
Yeah.
basically idea become money,
Yeah.
and so I think that from that perspective, that makes a ton of sense. Do you worry about losing access to the or losing connection to the hardware piece at all, or like is there any concern about that?
No, there's not, and we're not becoming an IP only company, right? We're using that
Mm,
as
yeah,
as an
yeah,
off ramp, if you will, for people that want to use the technology but don't have the means to do that themselves, and they want to license it for whatever reason, including their ASIC. So we're
yeah.
still going to have devices, but we'll have that ability for people to license that for their own as well. And actually, on the device side, something that's new that I didn't cover yet is something that we're doing with the Open Hardware Group. So they started by basically having this vision that they could have RISC-V cores that the community can use. They started with RISC-V cores that came out of ETH in Zurich, and oddly enough, or luckily enough, I guess for us, that's another story about these trade shows actually. So as a diversion here for a second,
Yeah.
I was at this Global Foundries event in Munich, and one of our guys in the booth was having lunch in the lunch the break room, and he met Frank Gernick from ETH in Zurich, and they were just chatting it up and talking about stuff. And Frank was like, "Yeah, we're doing these RISC-V cores, and we do all these test chips, and we're going to do one on 22 FDX, which is FDSOI process at Global Foundries."
Mm.
And the QuickLogic guy in the booth said, "Oh, you should come over to our booth, and we should talk about that because we actually have a 22 FDX IP core, an FPGA." So Frank came over, and we
What is sorry? What 22 FDX is a block like an IP block?
22 FDX is a 22 nanometer FDSOI, fully depleted
Ah,
SOI
okay,
process from Global Foundries. And
okay,
so
okay.
that's a
So
process that you can build wafers on
got it.
or with. And so we had already done a 22 FDX compatible embedded FPGA core.
Ah, okay. So you had already targeted. So you basically had already taken your IP and targeted it at this 22 nanometer process versus
Exactly.
a 45 nanometer, 90 nanometer, whatever else is out
Exactly.
there. Yeah.
Exactly.
Okay.
But we
Okay.
didn't have a device yet. We just had a test chip and we had the IP. And we were starting to engage customers. And Frank came up and he was saying all these great things they're doing around low power and looking at partitioning between RISC-V cores and FPGA cores. And we thought, what if we did something together where we donate one of the instances just for use for educational purposes to them,
Mm-hmm. Mm-hmm.
put it in a test chip with their RISC-V cores, and see what they could do in terms of hardware software partitioning for specifically for AI type applications. So literally, you hear these like handshake deals over lunch, right? So that happened. Uh, in that half hour that we met and we agreed that we're going to do that, they would go off and build that test chip and do all this research on it. And so that happened. They did the
Yeah.
test chip. They proved out these different use cases on it, and so that became the basis of what was donated to the Open Hardware Group for the RISC-V cores that Open Hardware Group is now sort of upgrading to be of commercial quality, right? And so now what Open Hardware Group is doing is they're upgrading the core for the RISC-V core, but they need a test chip to sort of prove that out. And so QuickLogic joined the Open Hardware Group in the summer of this year. Our CTO is now a vice chair of a working group there to help take that core and run it through a test chip on 22 FDX with our embedded FPGA. And that, you can imagine, could become a microcontroller in the future for QuickLogic that's now RISC-V based and embedded FPGA that would have a lot of different capabilities that we don't have today with our current microcontroller on that QuickFeather board you mentioned earlier. So
Mm,
that's
yeah.
sort of pushing forward the hardware evolution of what we're doing. Meanwhile, we're building out the sort of scalability side of the IP part of our business.
Hmm. Okay. I had a little bit of a brain freeze there. You had said Open Hardware Group, and so that is an IP group. I was thinking open source hardware group, which is a different thing. And names are tough. And so okay, so this is a IP group of like different industry players. It seems like. that are all working towards
Yeah, it's different industry players.
okay, open
Exactly.
source stuff like RISC-V.
Correct.
Okay, great. Yeah, that's really cool.
And then in sort of parallel with Open Hardware Group, we joined Chips Alliance, which is another industry group. And Google is heavily involved with that, and Micro is heavily involved with that. So that the Chips Alliance is focusing on IP cores and software tools that are ideally open source, so that the community can sort of have all these different pieces of the puzzle, so that they
Hmm.
can do their own chip design, knowing that what they're using is of good quality, gives you good visibility into what's going on because it's open source. And
Mm.
so
Yeah,
a lot of the
yeah.
Simplifo work, I think, is taking place within Chips Alliance, the RISC-V cores with Open Hardware Group, and it's sort of all tying together. And we have folks involved in both of those, because I think both of those are really important initiatives, both for us and for the industry.
Yeah, yeah. So Michael Gielda was on the show back on episode 519. He was also talking about Chips Alliance. We didn't get to talk about it too much, but yeah, it seems like a really interesting thing, especially because I mean, all this stuff being out in the open now, it seems like it would have been like a conference room at Intel or a conference room at Altera back in the day, right? It's like it just seems like it's really interesting that it is that the software focus of all this stuff has brought it into that open source, open development kind of realm. How has that been culturally? I mean, is there still a lot of pushback from other players in the industry, or is it just more like a lot of people are interested in it right now?
I think there's more interest than what people are willing to acknowledge from the company side.
Okay.
For us, because we're on the smaller side of the FPGA market, I think we have the ability and freedom to be a little bit more agile and take more risks, like what we're doing. I think if we're substantially larger and we're the gorillas in the market, like some of the other players, the ability to change or the desire to change is a lot more challenging. There's a lot, perhaps, of NIH mentality. There might be some view that, why do I need to change if I'm 50% of the market? Why do I need to
Right.
do that?
Right. Yeah. Yeah.
And why do I need to risk that? And so I think that there will be a point in time at which other companies are more forthcoming and actually contributing to the open source movement, like what we're doing. I
Hmm.
think for the time being, they're just willing to sit there and watch and wait until there's a tipping point where, the tipping point, I think, is going to be pretty clear. When they
Yeah.
start losing revenue,
That's right. Yep.
that's the point at which they're going to jump in.
Right. Or when their mailing list is 50% software people complaining about something. It's like
Yeah,
okay, well, ooh, yeah, we should probably do something.
yeah, exactly.
Yeah. Hmm. Okay. Interesting. Interesting. Can we talk a little bit more about the actual FPGA world? I suppose. I mean, like, what is your place in the FPGA realm? I mean, you mentioned you're a smaller company, but like, what does it take to kind of play in that market? Like, in terms of technology stacks and like things, I guess areas you're targeting and market segments you play in.
Yeah, so we focus on areas where power is important. It doesn't have to be battery powered, but ideally it's battery powered, or at least systems that do care about power consumption. We've been focused in that market for quite some time. And so the arrays that we have, the FPGA fabrics that we have, tend to be on the lower density side and very low power, able to implement things like different IO interfaces. You can do some lightweight processing in there. That's typically the markets that we focus on. There are other markets for FPGAs that are very data center centric, very high performance, high density. In those markets, you really have to chase the process technology curve, and so
Uh,
those are the ones where you're going to hear, 7 nanometer, 10 nanometer. Those are the ones where the mask sets alone are hugely expensive, like millions of dollars each.
hmm.
Those are really where the big players go. I think if you look at just in terms of the computing spectrum, there's the data center and then there's the edge. We tend to focus very much at the edge, where you do want customization, you do want computing, but you want to do it within the power envelope of something, not
Hmm.
where power is essentially free.
Right. Yeah, I don't traditionally think of FPGAs and low power. I mean, like yeah, obviously you guys do. There's a couple other players that are, like trying to target low power, but even then, it's a tough thing because you don't have like, you have to start having targeted silicon blocks to really have power down states and things like that to make it worthwhile on a battery.
Yeah, and we've done that. We have pretty granular control of clock trees and quadrants on the chip, so you can
Mm-hmm.
actually cut the power to save battery.
Mm-hmm.
I think in the future, though, there's this notion of heterogeneous computing. So I don't think that, just doing soft cores in a big FPGA makes sense. And when you're really looking at BOM cost and power at the edge, you're going to want some level of heterogeneous computing where you have maybe some small hard processor cores augmented by FPGA to offload or accelerate certain functions, which, by the way, is one of the use cases that test chip that ETH put out proved, that you could get substantial increase in performance or power consumption, a decrease in power consumption if you went with a more of a hybrid approach. So
Yeah,
for
yeah,
us, that's sort of the future, is more of this heterogeneous computing, augmenting processor cores with FPGAs, keeping in mind that for the edge, BOM cost does matter, right? So you can't just
yeah.
have $1,000 FPGAs and put it in an edge device. You're really going to have single digit kind of price points, very low
Hmm.
power consumption, like doing meaningful compute in less than a milliwatt, for example,
Okay.
and that'll really enable the masses.
Yeah, yeah. I mean, I mean, my FPGA days are pretty limited, but I do remember like the FPGA engineer being like, "Oh, look, we were on a Vertex 4 at the time." He's like, "Oh, look at this Neos 2 running on this $150 Vertex 4 part." I'm like, Okay, I get it, and it wasn't that good, but like, yeah, that the whole idea of like soft processors has always been interesting because obviously you're instantiating an entire processor internally. You can peek into what's happening there. That's all very cool and academic, but it's like from an actual needing a processor on a board, it's not as interesting, not as useful as I would, as much as interesting, I think. And so the fact that there is a shift back to hard IP, especially when it's RISC-V, I think that's very, very interesting. I mean, what is the relative scale of RISC-V? I still don't have like a good benchmark for the power or the capabilities of one. Is there like an equivalent like Cortex M blank, for the RISC-V that you have in that test chip, the 22 nanometer chip?
Yeah, that's a good question. So, because we're focusing on edge applications and lightweight computing, we tend to be more microcontroller oriented versus application processor oriented.
Hmm.
So, in our current chip, the one on the Quick Feather, it has a Cortex M4F with floating point unit. The one that Open Hardware Group is working on, they actually have two RISC-V cores. They have a MCU class and an apps processor class. So we're working with them on the MCU class one. So it'll definitely be more compute than the Cortex M4.
Hmm.
Maybe it's more like an M7 class
Okay. Yeah.
microcontroller from ARM. And
Yeah.
then I think the really interesting thing with RISC-V though is that anybody can sort of come out with their own extension to the instruction set. And in the case of what we're doing, since we have embedded FPGA on the same chip, you can imagine these other instructions you create could be offloaded to the FPGA core
Yeah.
to accelerate certain things like convolution, which is really important for AI applications.
Yeah. Yeah, again, I have very limited FPGA experience, but I do remember being very excited about like a C to H thing that was talked about at the time, or sorry, H to C or whatever it is. But basically, it was no, it was C to H. It was right. You were writing C, and then it would instantiate some hardware block, and then you could have like a special command. It didn't. Again, it just didn't really seem to do that much back then. But now with like the open tool chains, it seems like it's much more likely to have some more customizability, external peripherals that are very, very custom and, tightly coupled to the processor and enabling the low power, high processing kind of capabilities like you're talking about.
Absolutely. And in fact, just as an aside, so on the current device we have with the Cortex M4 and FPGA, we have that designed into some hearable applications. Hearables are like Bluetooth headsets that have some
Yep.
level of intelligence.
Hmm.
So we're working with a software algorithm company that does voice recognition. And their software engineers, I mean, these are like software DSP engineers, right? These are not, they don't know what an FPGA is. They don't know what
Hmm.
HDL is. So they were basically saying, hey, we have all these neat software algorithms, but we need an FFT to be less MIPS on my CPU because
Hmm.
it's maximizing all the MIPS and
Right.
memory available.
Just a lot of multiplies and a lot of accumulates in there.
Exactly. But it like
Yeah.
chews up the CPU, right? So
Yeah.
because we have the embedded FPGA on chip, we actually created an FFT in the FPGA and we
Mm.
gave them the bit stream and we gave them an API in C that they could actually
Oh,
call. So from a
yeah.
software engineering point of view, done deal, right? Just call
Yeah.
it an
Yeah.
API. We take care of the fact that it's running in the FPGA. They don't even need to know that, right? They just
Yeah.
see all of a sudden have so much more MIPS and memory available.
Yeah.
Now, that's us doing that design for them. In the future, with these tools in place, they'll be able to just write their code, take advantage of the fact that the tool intelligently offloads it to the FPGA like it was never there, and then we don't have to be directly involved. That's that scaling point I was mentioning earlier. So we
Mm-hmm.
don't have to be directly involved as a sort of a consultant on each and every design. And I think
Yeah.
the tools are going to get there, in the next couple of years to be able to do that pretty efficiently.
Are there going to be like guardrails for that sort of thing? Because the thing I think about is, or maybe it's more in the generation stage that I don't even quite understand. But usually, when I was working with FPGA engineers, they would be going and taking that block of IP that was generated, and doing simulation on it, making sure it hits all the timing necessary and things like that. Would it be required of the software engineer with this generated logic to then go and do that simulation and understand what they're looking at, or is it more like, well, it's just going to downscale until it works kind of thing?
Well, I think that sort of depends on the ability of that software engineer. There are
Mm-hmm.
engineers that can sort of cross that hardware software boundary and probably
Mm-hmm.
could feel comfortable running the FPGA tools to do the timing analysis. I think
Mm-hmm.
ultimately you will have intelligence in the tools that actually do give you those guardrails or boundary conditions, if you will, for
Mm-hmm.
how
Yeah.
fast or how slow they're able to run. And they'll be able to sort of propagate that back to the software engineers so that they understand that.
Yeah.
But in general, if you think about like audio use cases, in this case that I was giving, audio is relatively slow in terms of
Mm-hmm.
hardware
Mm-hmm.
requirements. And so that really shouldn't be a problem. It's where I think video is where you're going to start to see more pushing the envelope of power, where you'd really have to be mindful of that.
Got it. Got it. Yeah. So the wake word idea is really interesting to me because it's like, I remember, I think it was my parents that I'd gotten them like an Amazon Echo Dot or something like that. And I told them like, oh, it's so fun. You can change the wake word to computer or other like silly things. And they're like, oh, can we change it to, the name of the dog? And it's like, well, no, you get four choices, because that's what's in that front end chip there. It's listening for these phonemes that are waking up the chip and, at some
Right.
low power state. Cool. But there's no way to actually customize that because that is, I think in hardware, maybe it's an FPGA. I don't think it's any fabric there, but like to actually make that a wake word that is different, you would, that's kind of the, one of the applications you're talking about there, right?
Yeah. And in fact, there are tools now that allow you to customize the wake word. But
Okay.
just like any AI, your output is only as good as the amount of data that you throw at it, right? So if
Okay.
you just have one person, and by the way, our Echo in our kitchen, the code name is computer for that too. By the way, it's pretty funny. But it's a matter of how many data sets, how many people are speaking the wake word. Is it your 3-year-old versus you? Does it recognize the difference? All that comes to just how much data you
Mm,
throw at it. Now, in
got it.
our case, a lot of these chips don't have that hardwired because they recognize that these things are going to change over time. But with the FPGA, actually, what you can do is you can build more sophisticated models than if you were just limited by the processor, because
Mm,
you actually have more headroom on the compute side now, effectively
got it.
with that FPGA. And I think that's an interesting use case for us to tap into.
Yeah, and I guess you were also talking about a low power case. Like I'm thinking now about the Echo Dot that I have, and it's like that is plugged in, so that in theory you could put that model into a software realm and do that in software, but it might be very computationally expensive or software intensive in order to do that sort of thing. You're talking about, so the example you gave was a smart Bluetooth headset, so like super tiny, tiny low power kind of thing, and that,
Super tiny batteries
yeah,
and still wanting to be always on. So
yeah,
that's a huge challenge in terms of just physical space because of the battery sizes, but it can be done.
yeah. I always wonder what like William Gibson thinks about when he hears about all this stuff, like just, oh yeah, these devices wake up when this code word is said, and it's just like, oh man, it's just like a dystopian. It's a wild, wild world we're living in, Brian. It's great.
It is. It is.
It's like maybe we could like just make some warnings built in as the wake word. It's like, I know Jeff Bezos is listening to me is my wake word.
That's exactly why my parents will not install one of these in their house.
Yeah, well, yeah, we all take risks, I suppose. That's really cool. Okay, so let's stay on the audio thing and talk now about the QuickLogic Feather and the EOS S3 that's on there. So what is actually on? So this is a device that schmucks like me can buy today, and it's
Yep.
got a bunch of stuff in it. But what does it do, and what's it targeted at?
So when we designed QuickFeather, and there's a lot of Tim Ansel's fingerprints all over this,
Mm,
what we wanted to do is have a low cost open source development kit that wasn't just the device with a bunch of headers that forced you to go buy sensors and connect those. we wanted to put some sort of minimum viable sensors on there so you can develop sound use cases or motion use cases, because those are really common sensors used for edge IoT applications.
Yeah.
So we have our Quick Feather with our EOS S3, MCU, and FPGA. We have a microphone from Infineon, a pressure sensor from Infineon, and we have an accelerometer from MCube on there. So with all those, you can actually imagine all kinds of different use cases you could do for gesture recognition,
Mhm.
contextual classifiers for motion, vibration, and then the microphone and the pressure sensor could detect things like perhaps room occupancy changes, doors opening and closing, windows breaking, or voice recognition.
Yep.
And we've got a lot of partners that do wake word software so that they can actually run their software on the device, and you could program it to say any wake word you want, really, in different languages with those software partners, and then try it out on the board.
Okay. So like quick iteration as well. That seems like another important thing here.
Oh yeah, it's all about fast design iterations and trying to be as agile as possible.
Hmm.
And then in terms of the hardware side, because it's a Feather form factor, any Feather compliant peripheral board could be stacked on there. So if people are accustomed to certain sensors that are Feather compatible, they could just stack it up like a cake and reuse
Hmm.
the software they may already have in place to do those different use case developments.
That's great. I feel like there's always a disservice around like the so like it took me a long time to kind of figure out what people were saying when they're talking about like AI or I guess machine learning. I'm not even sure what do you guys say here? Is this like an AI type of thing? I just ML, is that maybe instead? I'm not sure.
Yeah, so it's for us, we talk about AI, and we have actually have a subsidiary company called Sensimal, SENSI, big M, big L. So it's like sensible machine learning, I guess you could say. And so
Okay.
that software entity, yeah, mouthful. That software entity, they were actually the software group within Intel when Intel was doing the Curie module back in 2015.
Oh
So
yeah, okay.
these were like sub $5, not sub $5, they're probably $5 IoT chips. And Intel recognized that you needed to have a software platform in place to make it easy to develop AI applications without being a data scientist. And
Mhm.
so
Mhm.
that software is cloud based. It takes labeled sensor data and it generates all these inferencing models that you could then run on device in a resource constrained microcontroller. At the
Mhm.
time, it was just the Curie. Intel killed Curie, but they had all the software.
Womp
So yeah,
womp.
exactly.
Yeah. Intel killed embedded platform. That story comes out about it every 2 years.
Yeah, I know. Dust off that playbook, right?
Yep.
So the core folks from that group spun out of Intel with all those assets and created Sensimal,
Mhm.
immediately porting
Cool.
to ARM architectures. And then we got involved with him as a partner company a couple of years ago. Ultimately, we decided it made sense to join forces, so we acquired them. But that software basically allows people to use QuickFeather and develop AI applications from labeled sensor data, program it back down to the QuickFeather device, and now you can start doing inferencing on device with QuickFeather
Yeah.
using the native sensors, or you can connect other sensors to the board and build models on top of that.
Yeah. I guess the thing that comes up with it though, like so the reason I said it like does it as a disservice is because like I kind of tune out when I hear AI, ML, all these things. But at the end of the day, like I don't know how I would say it better though. I guess that's the problem. But there is a ton of value there, and I think other people hear that AI ML thing and they just know what the value is. But it was took a board like this to actually, from my stupid brain, to kind of get an idea here. And I really like the idea of that door detection. I think that's a killer example because it is a sensor data kind of thing, right? It's obviously you're going to
Yep.
see some kind of spike there, but how do you tell that the spike is a door closing versus someone sneezing next to it? Like being able to actually like it's like a device classification or a sensor classification machine, and that's really where the value comes in. Without saying, I don't know, like saying AI and ML, like I understand that's what's underneath the hood, but I need something more like it's an answer machine. I don't know. It's my stupid
I,
brain.
well, no, I think you're really hitting on an important point, which is that I think when you say AI and ML, a lot of people find that overwhelming if they don't have a data science degree, right? But a lot of people know what's going on around them. They're domain experts, like the door closing. If you were to
Mhm.
have a quick feather board or any board for that matter, and just start opening and closing the door and looking at a waveform on a screen, you
Yeah.
know when you were closing and opening the door. right? So you
Right.
can label that data without even knowing what the data is. And then
Right.
how you
I
translate that to something else is what the tools can do for you.
Yeah, I think the real problem is that when I think about how I would go about like detecting something like that, I would probably set up simple thresholds, or maybe if I'm really feeling my programming prowess that day, I try and do like some kind of slope detection on data or something like that. But that's me imposing math on a very natural phenomenon and trying to make sure that my math fits it, and it'd be just like a lot of guess and check, whereas these methodologies of AI and ML are actually just like, we just start with the answer and then you work backwards to the algorithm that detects that. And it's, I don't know, I just feel like that would really play better to hardware people, because it's like, since threshold detect doesn't work well enough, this thing does.
Yeah, and I think navigating that space of what is the right math function to actually yield the result, that is like the old way of doing it, right? You're a DSP engineer, you have the signals, and you start applying all these different functions to it to see if the output is going to give you good
Yeah.
results.
Right.
And it is very much flipping that around and saying, no, here's the output I want, and then the
Yeah.
tools take care of that for you. That's really auto ML, right? It's
Yeah.
using
Yeah.
AI to create AI.
hmm Yeah, like neural net interface inferencing and stuff like that as well, right? Just
Exactly.
like being able to get a percentage fit. So if you have now, like, I don't know, the door closes and it causes like a big spike and then like a gradual decline and then a little dribble at the end or something like that, you can tell how likely it is to fit that model. Or I guess the other thing that's difficult about something like that, when you start actually looking at the waveform in a graphed manner, it could be compressed more because someone closes the door faster, or it gets spread out because they're closing the door slower, and it's just like
Or
all of
maybe
these
there's
things in there.
maybe the front door is open, and so closing the door is actually
Yeah.
easier, right?
Right,
Yeah.
right, exactly. Yeah,
Yep.
it is just, there's so many permutations that I don't know, it's just like a time saver. It feels like, or I don't know. There's some magic. There be dragons there, but there's also some magic.
There is.
Yeah.
There is. Yeah.
So how do people go about then using the sensimal? Is that right?
Sensible. Yeah.
Okay. I'm gonna be honest, Brian. Not my favorite name, but I get it. I get it. I get how it goes. Uh, how do people actually go and do that then? You mentioned it's cloud based. So is it like you just upload someone closing a door 100 times and pulling the data out, and then it spits back some code?
Yeah. So the simple way to do it, and we're actually, just to give a plug, we're doing a Hackster.io contest right now around global climate change. And you
Cool.
can apply for free hardware and get a quick feather and a community edition of Sensimal. And you basically can use that to capture sensor data, build models, and do a proof of concept. So
hmm hmm
the way that this works is that you would get a quick feather board, and there's a USB connector on there. So you can just connect it via USB to a PC. Alternatively, you can connect it with, because it's a feather form factor, you can connect an ESP32 Wi-Fi Bluetooth module to it. And we've proven that
Oh,
out.
yep. hmm
So you can basically stream sensor data over that to some Wi-Fi connected device. So with that, you basically start collecting data in the use case that you're talking about. So in your case, maybe you attach it to uh, somewhere around the room near the door, and you just start opening and closing the door and capturing the data. You label it. So you're on your screen. You could just imagine seeing this time series data, and then you would just start segmenting that and say, okay, this is when the door opened. This is when it closed. This is when it opened. This is when it closed. It uploads that to the Sensible cloud, and then as more data comes in, more data sets, then you can start building a model. So let's say you have you've given it to a few friends, you've gone to a couple of houses, you have like 20 data sets now of doors opening and closing over the span of a few minutes, right?
hmm
What you'll get back from Sensible when you say, this is when you use the analytics toolkit, it'll actually give you certain classifiers, models that you would then run on device. And it allows you to dial in performance and power expectations, right? So it gives you a few choices using these different algorithms, different memory, different MIPS, and then you choose which one you want. And then at the end of the day, when you choose that, you get an image, a binary that you can then flash back down to the device, to the quick feather, and then actually try it in system now without it going back to the cloud to give you the
Yeah,
answer.
that's super cool.
And if you, by the way, if you get more data over time, let's say you go to a few different more houses, you just upload that data and it sort of retrains the model with that additional data. So perhaps it gives you a more accurate model or perhaps a smaller model because it's got more data to work with. But it's an
Yeah.
iterative approach.
Huh. And what are the limits of then? Okay, so now we've got the door data.
Hmm.
Does the data have to be in a certain format in order to make it useful? So if I go and put like a barometric sensor, no, you already got, well, I guess you've already got that, but like say that now it's like a high pressure sensor and I want to hook this thing up to my scuba tank for
Hmm.
God knows what reason. And I want to track the scuba, pressure valve kind of stuff there, but it's not actually on the quick feather. How do I go and format that data coming from a sensor to actually pull it into this same ecosystem to make it like a custom thing then?
It's really straightforward. So at the end of the day, all of this is just time series data, right?
Okay.
It's
All right.
data over time. And so, I mean, you could even overlay it with stock data, right?
Oh, great. Yeah. That's what we need. We need more robots trading.
No, I know. I say that tongue in cheek, but
No.
that's really all it does is it sees this as time series data. It doesn't matter what it is, and you can
Yeah.
basically just tell it. You can label it what kind of data it is. You can say this
Oh,
is the
cool.
pressure data, and if you had a temperature sensor, you could say this is temperature data. We have certain examples on our website that connected a PM 2.5 sensor with the feather form factor, so you could do AQI, air quality index. Again, that's just time series data, much like what we're looking at right now, which is just our microphone data spiking around
Yeah.
as we talk. Right? It's all
Right.
the same
Exactly. Yeah.
thing. All
Yeah.
it's looking for is patterns in that. It doesn't need to know that it's specifically temperature or sound or motion. It doesn't
Mm,
care. At the end of the day, it's just a waveform looking for patterns.
that's great. So
Yeah.
then, okay. So now we have this model. It gets loaded back down onto the device. I have two questions about that.
Mhm.
One, how does that get implemented then? Is it again, like you mentioned, just an API that we would be able to call from a program that we're writing for the processor? And then the other question is, how much resources does it end up taking up based on that dialing in you mentioned with the on the sensimal website?
Yeah, so I'll answer the first one first. So the model is basically it's just a binary. It's a library that expects a certain input, which is your time series sensor data. Usually, it's going to
Okay.
be probably 16-bit data of some frequency, 50 hertz, 100 hertz, whatever. And then the output is just going to be letting you know what classifier has been triggered. Right?
Oh yeah.
Is it running? Is it walking? Is it door open, door closed? You can label those, and so you're just plugging that model, that box, that black box into your C code. Now, if you use our Quick Feather, we have this thing called Quark, QORC, which is our QuickLogic Open Reconfigurable Computing package, or SDK, if you will. It has FreeRTOS. We also have Zephyr. So those operating systems already are going to sort of abstract the hardware details, and you can just say this is accelerometer data or microphone data connected to the model you get from Sensimal, and then the higher applications can then take the output of the Sensimal model.
Huh.
Now, the size of the model, which was your second question, that really depends on your performance requirements and the use case. So, like very low data rate applications like temperature, which doesn't change very frequently, or pressure. And if you only are trying to classify a couple of different things, like the threshold example you were giving earlier, that's probably just like tens of kilobytes. It's just going to be a small, not challenging model, or not really exercising too much of the capacity of the device. If you're going to go for something a little bit more beefy, like let's say you're using a lightweight image sensor and you want to do human presence detection.
Mm,
Okay, well,
yeah.
human presence detection obviously is going to be a little bit more sophisticated than just temperature variation, and so that's going to probably start pushing the model up to, high tens, maybe hundreds of kilobytes on the model. So it's very use case dependent, but it does have the ability to actually get very very small in terms of consumed resources.
Hmm. Okay. And then where does it run? So I'm looking at the block diagram of the
Hmm.
EOS S3, and it's got an ARM4 or Cortex M4. It's got some sensor manager stuff. It's got
Yep.
DMA. It's got SRAM. All these other things. Low power sound detector, and then it's also got eFPGA in there. So does it run in the FPGA, or is this a data block that's running on the Cortex M4?
So the output from Sensimal today runs on the Cortex M4.
Okay.
And it's not just our Cortex M4. We're very clear that when we acquired Sensimal, we wanted them to be able to port to anybody's processor, right? It just makes more sense for that to be
Yeah.
freely running on anybody.
Yeah.
Now, so that's the default. The roadmap is that they will actually be able to have those APIs I was referring to earlier for that Hearables customer be able to target the embedded FPGA to offload things that should be offloaded. and that's something that's going to be automated over time. But right now, it's still a sort of manual process where if we say we want to offload to the FPGA, then we would provide the IP for that, the bitstream for that, and then the API for that to the customer.
Hmm.
Now, in the case of human presence detection, this is one of the use cases of TensorFlow Lite for microcontrollers, and one of the sort of talked about use cases, I guess, and researched use cases. So we've actually proven with that test chip from the ETH that's now being run by the Open Hardware Group that you can actually take the output of TensorFlow Lite, which calls convolution as a core function for sort of the heavy lifting of the
Mm-hmm.
inferencing.
Yep.
We've provided APIs for convolution that offload that to the embedded FPGA. So we still have to modify the high level code to call the FPGA instead of just using the RISC-V processor for that. But that, again, you can imagine over time is going to become more automated.
Yeah. Yeah, exactly. Yeah, that's interesting. So, so then, okay, so the model that people might download from Sensimal it's going to be running on the Cortex M4 for now. That's great. In the future, you said it might be running through this API that's in the FPGA. But if
Correct.
people wanted to use the and it's called eFPGA, so maybe whatever that is first. But then how much capability is in that FPGA fabric that's around this thing? Because I remember when I was looking at this QuickLogic board, I'm like, wow, there's a lot of stuff on here. But the FPGA stuff was probably the most curious to me that it was in there, aside from the fact that you guys were making it.
So eFPGA is embedded FPGA. So if there's a FPGA core in a bigger processor, we typically would call that an eFPGA. FPGA is when the whole device itself is primarily just an FPGA device, a discrete
Okay.
FPGA.
Mm-hmm.
So because we have the ARM core and all those other things, it's really a core among many on that chip. And so we refer to it as the eFPGA. So the eFPGA in the EOS S3 is it's between 1,000 and 2,000 logic cell equivalents. And that's the reason why I give a range is because different logic cells have different utilization depending on which competitor you're talking about.
Yeah.
So generally we say it's 1,000 to 2,000 logic cells. What you can do with that, you can do additional interfaces to different sensors. You can also do things like the FFT I mentioned earlier because we have some very tightly coupled math blocks with those logic cells. And so now you can start imagining some of the math functions that you could do that don't chew up logic cells will be used in the math blocks.
Mm-hmm.
That's the capacity of that device today. The one that we've talked about with respect to RISC-V and the Open Hardware Group, I think the logic capacity goes up by like a factor of 6 in that one. And the math blocks get actually quite a bit more capable. So the compute capability of that roadmap chip is, I don't know, probably like 10x what we have today in the
Mm-hmm.
EOS S3, which is exciting for the future. But today, I think EOS S3 is very capable for doing some very lightweight inline signal processing or offloading from the ARM core or additional interfaces that maybe you just didn't have
Yeah.
in the hard logic part of the chip. For
Yeah.
example, this is really
Yeah.
cool actually. So USB, right? Everybody thinks USB needs specialized hardware, and most people do it that way. They license a USB core, USB PHY, and they dedicate the silicon to that. So EOS S3 does not have a dedicated USB core. But through this whole initiative around open source and talking with Tim Ansel and QuickFeather, we've actually implemented a soft USB core in the FPGA, which is amazing. So that
Yeah.
the FPGA pins are what's driving that USB connector on QuickFeather, not a USB hardcore. And that
Huh.
just speaks to the sort of capability that you have with embedded FPGA these days.
And so how much give us a relative size then? Is that like 50% of that logic, or is it the entire thing?
It's somewhere between 30 and 50% is
Uh-huh.
occupied by that USB core. And it still gives you some logic available for other things.
Uh-huh. And that's like USB 2.0, like up to 480 or
No,
12.
it actually reverts back to I think the 1.1 as full speed mode, not high speed mode.
Got it. Okay.
But for transferring data to and from the device, it's adequate.
Yeah, I think that's right. And I mean,
Yeah.
like a lot of people, like people are doing that now as well with like tiny USB. I think that's how
Yeah, exactly.
Luke does that on the tiny FPGA.
Yep, that's right.
Yeah. So,
I think a lot of that work wound up in QuickFeather as well.
oh, cool. Okay, that's great. Yeah, yeah, it's amazing that kind of stuff that's out there, but it's really useful to have that kind of flexibility. So,
Yeah, it is.
so then people targeting that eFPGA right now, is that so that's using the SymbiFlow uh,
Yes.
toolchain, everything like that?
Yep, exactly.
Okay. Do you guys have any like videos on I'll be honest. I've done a couple workshops on the FPGA stuff and all the toolchain workflow stuff. I get so as a hardware person, I get so locked up just like because it is such a software centric workflow that I'm just
Hmm.
like, oh God, what are these people doing here? But it's not hard. It's just I think intimidating at the beginning. So I always like to have like a you know video I can go back to and watch. Is there resources out there like that?
Yeah, we have videos and we have really clear step-by-step instructions in our GitHub repo
Okay.
that I could send you offline. But and it's to the point where I've even been able to run it. I mean, I did this 20 years ago. I
Hmm.
stopped designing for a long time, but I was even part of the QA to make sure that dummies like me could run through the tools and get them up and running and run a design.
That's really important, I think, and that kind of friendliness. I feel like that friendliness maybe especially in the FPGA world, but it's like there is a high cost to doing business in the FPGA world in terms of like using FPGAs, and I feel like that's kind of a point of pride for a long time. It's like, oh well, you just kind of have to do this, but it's definitely migrating in that friendlier way of doing things, and that's going to bring in more customers, like you've been talking about. I mean, there's so many more software people out there than there are FPGA people, and the FPGA people are still needed because there's a lot of difficult things to do still. I think so. It's kind of win for everyone from my perspective.
I agree. I mean, we graduate like 10 times more software engineers than hardware engineers. So, yeah, if you can make it more appealing for the software engineer
Hmm.
and more usable, then you really are going to
Right.
proliferate the technology much further. And I agree, there's still a role for the FPGA folks to play because
Yep.
you are going to need optimizations and you have to understand, how to get the most out of the hardware, and they're going to be able to provide that guidance.
Yeah. And then there's still, hardware people still have to be around to be like, well, actually, no, you do have to put a resistor on your LED, folks. I mean, you got to
Right.
do that. Yeah, that's been a common discussion lately.
Yeah.
I got to say, like when I think about all this stuff, I mean, one of the things I always think about with demos or test boards and things like that, it's often a making something look good to your boss is a very important
Hmm.
important like threshold to cross. And I can just imagine that using like the sensible tools and stuff like that, it's got to have some wow factor in there. I mean, just being able to detect these different capability or these different events happening in the world, it's got to be pretty shocking in terms of uh, the capabilities of a board like that.
Yeah, I think it is. And we've engaged with certain customers where they have Quick Feather. They've watched the 1 hour tutorial video on how to use that with Sensimal. And it really gives them now the capability to build a proof of concept for like $50, right? Because our board is
Yeah.
$50 and our Sensimal Community Edition is free. So for $50, they can go into their labs, connect it to the whatever system they're trying to do this on, build a proof of concept, and then, like you said, take that to their management team and say, look at what AI can do for us, and then
Yeah.
run through that ROI calculation and see if it makes sense to move forward at that point. But
Yeah.
yeah, I think there we have to, as an industry, we have to make it easier for people to build proofs of concept around these types of capabilities, so it can really start taking hold. Because it is
Yeah.
intimidating if you're not a data scientist or not an AI professional. It's intimidating.
Yeah. Yeah. Well, let's talk about cost as well. So the board is $50, like you said. What is like the 1K price on an EOS S3 if we wanted to go buy one?
Uh, Generally, don't like to talk about pricing too much, but it's depending on the package, it's a few dollars for an EOS S3
Okay. So does that
for
mean that
that
you're
for that
not
type
in
of quantity.
distribution anywhere though?
We do have it in distribution. We have distributors around the world, actually, Future, Avnet, different ones in Asia.
Uh huh.
We're in the process of bringing on another distributor that I think is going to be very friendly for the community in terms of open source and easy access to hardware.
Uh huh. Uh huh.
Name TBD. But yeah, I
Okay.
think the one key piece price for them is going to be in that few dollar range, depending on the
Okay.
package.
Yeah, I think that's that's what we talk about on the show when Dave and I talk. Sometimes it's just like until it's on a distributor site and I can buy it next day, it's not really a thing. Like, of course, it's really a thing. It's out
Right.
there, you can buy it, whatever. But being able to just throw it into a design is, yeah, that's I think just another acceleration factor, right? Of just being, hardware weenies like me can go and buy one and put it on a board and just try it out. And like
Yeah.
you said, you can try it on a quick feather right now, and that's an even faster way to do it. But I think then taking that next step to getting it designed in is like a really key thing as well.
Yeah. And since we've launched QuickFeather and we put all the schematic files out there and the data sheets and whatnot, We've actually seen already a few other folks do their own versions of that
Uh-huh.
or
Yep.
modules with EOS S3 that could then be put onto a dev kit,
Hmm.
sort of making the PCB rules a little bit more flexible for the dev kit.
Yeah. I mean, I'm literally looking at it and I'm like, oh, I wonder if I could make a little add-on for one of my boards. You know, like, it's just
Yeah,
like I think that's just kind of like how we think about it. Like, oh, could I put this in here? Could I put it in there? And the capabilities it offers, I mean, like that's a pretty killer tool in the toolbox.
exactly. And that sort of circles back to that notion of mass customization, right? The fact that you like
Hmm.
thought about that and then can actually do it, that is exactly mass customization, which is what these
Hmm.
tools enable.
Yeah. What about on the sensible side of things? So you mentioned there's a community edition that's good for the Hackster contest, like you're talking about. But is it going to be like, is that where licensing comes in then? It's to actually take something in production using the sensible tools?
Yeah, so the community edition is not just for the Hackster contest. It was created in
Hmm.
conjunction with that, but it's really for anybody. So if you
Okay.
wanted to design, I would recommend you use community edition as well.
Hmm.
So if you start to do models where you're actually going to be deploying them commercially, that's
Yeah.
when you start using the Sensible tool as a real SaaS tool, and so there's a
Okay.
subscription for that.
Ah, okay.
And generally, that also ranges with the type of sensor data and how much data you're storing, how much data science consulting you may need to get what you
Yep.
want out of the tool. And so that can range anywhere from, like $1,000 a quarter up to $20,000 a quarter, depending on, again, how much you actually need help and how much you need from the tool itself.
Yeah.
But it's very affordable, very easy to get a model going and to get it into some level of production as well.
Yeah. I mean, so and thinking about like the paid subscription type of thing, is that like as long as it's in production, you kind of need to maintain it, or is it more like you need to maintain a license or a subscription in order to continue to make new models? Like, so once I make a model,
It's really for making new models. It's really for
okay,
making
all right,
new models. And I think the notion of AI is that, again, the more data you have, the better your model is going to be over time.
yeah, oh
So
yeah,
most likely, like our experience is when companies start to use that from a SaaS point of view, they don't tend to stop
yeah, oh
because
totally.
they are doing that evolving design, but it's
Hmm.
not required.
Okay, yeah, that's great. I think that's the thing that makes my hackles go up usually is just like the idea that it would potentially disable a hard piece of hardware, like
Oh,
if I
no.
don't continue to pay for access
Yeah,
to that thing. But it sounds
definitely
like
not.
that's not the case at all. The other thing that's nice about it, I mean, like we talked about, it sounds like Sensible, like the value proposition is basically replacing the DSP engineer in that case, right? Because it's classifying, it's being able to like pull in sensor data, classify the sensor data, make a model for it. Basically, that is what a lot, not exclusively what a DSP engineer does, but like that ability to do that is is key to that functionality, at least from my experience, and being able to like maybe not replace a DSP engineer, but like to allow a smaller company like or a consultancy like me to go and like get access to that sort of thing without hiring out to $150,000 salary. Like that's powerful. That's worth paying for. Like there's some real
Yeah,
value there. So that's easy. It's easy math, I think, at that point.
I agree. When Sensible was still part of Intel, they'd done a study around this and to identify how much money am I saving my customer by using this tool.
Yeah,
And it was
yeah,
around $500,000 in people costs because, yeah,
yeah.
the DSP engineer certainly has to be involved, but there's probably some level of data science engineer that you'd have to hire. Those
Oh
tend to
yeah.
be very expensive folks.
Yep.
So when you add all that up, it's like $500,000 for even getting a proof of concept pulled together that you
Yeah.
can now offload to this tool for essentially free for the community edition before you actually decide, yeah, I'm going to build a real product out of this.
Yeah. Are there any other restrictions on the going to like product? Like, do you need to get like a license agreement in place to actually push something out in the world?
Before you go to a commercialized model, yes.
Okay.
But as far as doing proofs of concept, you can do that all day long with community edition, and there's no,
Yeah.
legal hurdles beyond the click through that's on the website.
Cool. No, that's great. I mean, like, yeah, and like I said, I mean, my mind is spinning right now in terms of, it's not just your boss. Sometimes it's your client, right? So I have
Yep.
clients that I want to try and impress and, to win jobs and things like that. And I'm taking sensor data all day long. And usually it just kind of sits there. Obviously I can
Yep.
do thresholding and all this other stuff. But if I can make it do cool things now, I can win more work. I can, show my quote unquote expertise. Like it's just like
Yeah.
my brain starts ticking around all these things, and I assume that all the listeners out there are thinking through it too. So that is really cool.
And actually, on that, you just reminded me of one really cool story. So I can't remember if it was Quick Feather or a different board, but it had several different motion sensors on it,
Mm-hmm.
including gyro and accelerometer. And hardware engineers know gyros take like 10 times the power of an accelerometer. So
Yeah.
if you if you can get away without using the gyro for whatever you're doing, you're going to have longer battery life, right? So this customer came and said, "Hey, we want to do these gesture classifications. Here's Excel, here's gyro data. Tell us how many MIPS in memory and power and so on." So we looked at it, we ran it through the tool, really easy. You could do this yourself. What we found out is that the accuracy of the gesture detection didn't change if we removed the gyro from the equation.
Wow.
And that was
Yeah.
that was possible because we were able to do this in software super quick. So then we go back
Yeah.
to the customer, and now to your point, like as a consultant, you're adding a lot of value because you're saying you don't need to buy $1 gyro
Yeah.
that's going to kill your battery life. Just use
Right.
accelerometer, right?
Right. Or even going from a 6 degree of freedom to 3 degree of freedom, like you might save
Exactly.
BOM costs that way too. Yeah. That's
Exactly. Yep.
wow. That's really cool. And when you say gesture detection, like what's an example of a gesture detection that might be out there? Is it like waving high while you have like a wristband on your wrist or something like that? Or
Those are the probably the most easily understood is wrist worn wearables. So you have,
okay.
rotate your hand to look at the face of the watch.
Ah,
You
okay.
can do like double tap where you want to activate the screen.
Hmm.
Those types of things where they're detecting that movement. Another
That's
gesture
done with
could
that's done with an accelerometer, not with the cap touch on the screen.
sometimes those are cap touch, but you can actually do that with accelerometer too.
Oh, that's interesting.
Double tap. Yeah.
Yeah, my wife has a Apple Watch, and yeah, it's got like a bunch of gestures and stuff. But I don't get how any of that stuff works. It's just like, oh yeah, okay, okay, yeah, cool, it's doing a thing. Wow, okay,
Yeah.
and I guess that it would. I mean, yeah, I guess, yeah. Thinking maybe that's a really good, a hard example or like a visceral example too. Like thinking about like rotating a wrist to turn the screen on. Right, that's like one of the things the Apple Watch does, and I can just imagine all of the different ways you might be rotating your wrist and you don't want it to turn on, or you do want it to turn on, and if it was just a generic, you know, seeing gyro data in a certain axis, just seeing a rotation in a certain axis, it would give a lot of false positives, I would imagine. Whereas a, a algorithm that's generated from a lot of user data would remove some of that.
Yeah. And this is also where you can blend in some other contextual awareness, like are you left-handed or right-handed? Right. Because the
Oh, wow.
how
Yeah.
how it plays into that depends on how you're wearing it.
Hmm.
Or if you're a child or an adult. Like we all have different ways of doing interaction with our devices. But you can build a lot of that into the model if you use the AI because you don't have to look at the waveform and do it by
Yeah.
hand.
Yeah. Yeah. I mean, I always think about the industrial. So, like, I'm in the industrial space, and that's what
Mhm.
I think about. And talk about a industry that has not seen any of this stuff yet, but I feel like it is just ripe for it because I mean, there's a lot of startups out there doing that, and I know some of them. They're doing some very interesting things, but like, yeah, there's just so many interesting industrial applications that are just on the precipice of using this sort of stuff. And boy, I hope I get all the contracts to do that, Brian. I gotta say.
Well, so for me, industrial is actually the bigger market here for this
Yeah.
technology
Yeah.
because
Yep.
this is where it's like you were saying earlier, it's sort of an old industry, it's traditional industry. These are big pieces of equipment in a lot of cases. They have very unique sounds and vibrations,
Mm-hmm.
right?
Mm-hmm.
Those are all time series sensor data. And in
Yep.
this case, the technician probably can like put his hand on the machine and listen to it and tell you what's wrong with it, right?
Mm-hmm.
That person can now use AI to create these classifiers. They can
Yep.
label the data because they know what's going on with the machine at that moment and create the AI. So you don't have to pull in all these other folks to build that model. To me, that's really powerful.
Yep. Oh yeah. I mean, totally. I always forget his name. I'm so sorry about this to the person who I'm about to talk about. But we had someone on a long time ago, and he was doing this kind of thing where he was basically he was just doing current sensors onto the press machines that were in like Detroit auto factories. So these $40 million presses, and he was just detecting when they stopped spinning. And it's like that alone had a ton of value.
Right.
Uh, but now they could take it and actually do more with that data and actually put accelerometers on there and see how
Yep.
hard the thing is slamming down all these other things. And it just feels like that application was just a little too early because this was like 6 years ago, I think. I
Wow.
feel really bad. I never remember his name. Jerry Roston. There we
Oh,
go.
good memory.
Yeah. It just popped in my head, I think. I hope I'm right. But anyways, yeah, that sort of thing. And like that industrial space is just so exciting. I don't know. I
Oh, it is. I agree.
yeah. There's a lot of money to be made there, folks. So stay out. I want it all. And Brian does too, of course, of course. Yeah, this is very exciting. Where else do you see? I mean, industrial is one space. Are there other spaces that you're thinking are going to benefit from this in the future?
Well, our focus in the last several years have been around consumer. So we're
Hmm.
going to continue enabling things in there. Industrial is something we've started to refocus again in the last year or so. So I think the industrial is going to start to take hold from sort of end of this year onwards because the design cycles are much slower. Programmable logic in general has a lot of use cases in automotive, in military. We've got a big business in military defense customers that like to use programmable logic
Mm,
for whatever reason. So I
yep.
think we're going to start to see that sort of come back in
Hmm.
terms of new designs as well for us in the future, especially as we think about this whole IP licensing strategy.
Mm.
And there's a lot of research around how AI can bring value in automotive for safety applications, autonomous driving,
Oh yeah.
and then military, obviously, for a lot of different reasons. So I think this it's almost endless. The one thing that we're just sort of steering clear of is data center because that's well
Oh yeah.
served
Yeah.
by many people. Even if you take out the power equation, there's just so many people in there already. It's that red ocean. We're focusing on these other areas where I think we have a lot more value.
Yep. That makes sense. When you mentioned the IP business, that is something you're doing today, but that would be then would that be taking some of these models as well and putting them into silicon? Is there ever that thought to make it like a hard IP block from known sensor data, or is that not really in the cards?
Doing hard IP data for things that come out of the sensimal tool, probably not because they change so much. But I think that if you think about like TensorFlow Lite, and by the way, Sensimal has an integrated workflow now with TensorFlow Lite for microcontroller. So people that are
Hmm.
familiar and want to use TensorFlow Lite can do that within the context of the Sensimal tool.
Okay.
There are some specific functions that get reused a lot, like convolution, right?
Okay.
So we probably will. We're doing that now, in fact, where we're using the logic and the math blocks to efficiently implement convolution. I think as the state of the art changes and who knows what's after convolution, we'll look at how our architecture could be augmented with blocks to run those better. But I don't foresee it being a hard coded thing for the whole algorithm just because that sort of takes away from wanting to change and evolve the algorithm over time. It moves too fast.
Got it. Got it. Okay. So what are some of the blocks that do you have like publicly known IP blocks that you sell today, or is it more kind of under the hood and with agreements with other vendors that you sell?
Well, today what we license is the arrays of logic cells, and then we
Okay.
have the option of doing memory blocks and or math blocks as well if they're wanting to do some sort of math-oriented functionality.
Got
Beyond
it.
that, I
Okay.
think there's other things we could do in the future, but we just haven't discussed any of those things publicly yet.
Okay. Yeah, that's great. That's really interesting too because I mean, as more people are getting into this, obviously we talked on the show about the open PDK and things like that. It does seem like someone might be like, well, actually I need 5 RISC-V processors and I want
Yes.
a little bit of fabric in there and I need a whole ton of memory and like but then it really becomes ordering off a menu and obviously
Yeah.
putting it all together and simulating whatever, but it's yeah, it's an interesting business. Do you see that do you see that is that going to be a core growth as well? Like, are we going to be seeing QuickLogic memory and logic fabric popping up everywhere?
Memory, I'm not sure because there's so many different ways of doing memory. But
Hmm.
logic and how it interacts with those blocks, I do think you're going to start to see things from us popping up much more frequently than you have in the past.
Yeah, and so then okay, so now I'm just going to play a hypothetical.
Hmm.
Company X goes and puts down the Cortex M33 or something like that, and they license some QuickLogic fabric. Are
Hmm.
they and it's their own product? Are they then using the same tool chain that the SymbiFlow tool chain as well?
Yeah, and in fact, I'm glad you brought that up because I think one of the sort of the speed bumps, if you will, for people to use embedded FPGA or license embedded FPGA for their own chips is that
Uh-huh.
if you have a proprietary tool chain and they're licensing this from us and then trying to sell that to their end customer, how do they
Yeah.
support that whole thing with somebody else's proprietary tools? With the
Right.
SymbiFlow approach and it's open source, they could actually integrate that into their own SDK, right? They could white
Yep.
label it whatever they want, company X product. Now it looks like an integrated development environment for their customer. And I think that
Mm.
really makes it a more appetizing way of doing that support for them.
Yeah. No,
So I think
that's
it's a huge enabler
great.
for it to be open source.
Right. I mean, that's like when people started switching over to Eclipse-based IDEs, and they're like, instead of like being like, oh yeah, we had 2 interns write our IDE, it's like, no, we're using Eclipse, and yeah, we know it's Eclipse, but it at least is Eclipse.
Yeah,
I don't know,
exactly. It's
but
well
it's a
known, well
big
understood.
shift. Yeah,
Yeah,
yeah.
exactly.
And then then I think there's extensibility within that as well. You get Eclipse plugins, or you get other interactions that you don't get to determine the entire flow of things, but also you don't have to. And that's kind of it seems like that's kind of a nice thing that it's surprising that it's taken this long, but I'm glad you guys are taking that leap. That's really great.
Yeah, choice is very powerful.
Yeah, that's great. Yeah, and I mean, choice is powerful. I think having good examples is important too. And so I think having like reference platforms like the Quick Feather is a great starting point for people too, to just see it's not super scary. I've yet to try it myself. I might have to try and enter this Hackster contest. I've also never entered a Hackster contest, so we'll have to see if I can pull together the time for that sort of thing. Where can people find out more about the contests and the boards and everything about QuickLogic and the platform?
Well, if for the Hackster contest, you just go to hackster.io, and it's a community-run contest that's right on the homepage above the fold, so it's pretty easy to find. It's the Global Climate Change Contest, and it talks about
Mm-hmm.
Quick Feather. So
Great.
pretty straightforward there. There's actually a landing page from that to a QuickLogic page that goes over all of the resources available for designing with Quick Feather and with Sensimal. So it has board documentation, chip documentation, video tutorials with Sensimal, so you can kind of know exactly how to plug in the board, get it up and running, and start collecting data. In addition to that, there are several web pages or sites that we have on EOS S3 on our products page. Quick Feather's there as well. And then there's a lot of sort of cross-pollination between that and the Sensimal website. Sensimal actually has a lot of good video tutorials, like chapter by chapter, on how to do the different steps from getting the board up and running to data collection to model generation to flashing the device, and even the test app that they have that allows you to test in device or in an Android phone.
Awesome.
All on video. Basically, you can watch at your own leisure.
Yeah, that's pretty much the only way I can work. I don't do well with written tutorials. That's very much appreciated, because then I can like slow it down. I'm like, wait, what did they type there?
Yeah, I do the same thing.
Yeah,
Pause.
yeah. Well, Brian, this is an exciting future you guys are painting. I'm very excited for you, and I'm excited to look like a rock star to my clients. I think that might be the best thing out of this.
Yeah, I think your clients are going to like what you do with our products, and I was so excited to come on. This is my first podcast with anybody, so I've enjoyed it.
Great.
And I hope people find it entertaining and learn something and feel inspired to join the climate change contest. We'll see.
Oh, okay, I'm sure they will. Are you online anywhere people could find you, or?
Yeah, you can find me on LinkedIn for sure.
Okay.
Ping me there, or I think my email address is fairly public now with the fact we're a public company. It's my last name at quicklogic.com.
Okay, great. Well, Brian, thanks so much, and we're looking forward to seeing what you guys do next. Thanks for all the open source stuff you're supporting and being part of.
Thanks, Chris. Appreciate the time today.
If you like community-supported projects like the open source toolchain for FPGAs, you'll be glad to know this program is supported by the Amp Hour Patreon community. You can join the others at patreon.com/theamphour and get invited to our private Discord chat server. A special thanks today to our corporate sponsor, Vino.